Hi, this is Cian McCue again for the final project piece of our fall semester of ME 272 here at IUPUI. So to add and kind of what will be different about this project compared to the part 1 and part 2 is that we are really going to dive into the beam deflection portion of the load that we found in part 2 of the project. On the locomotive on railroad track, the background from the previous project was from used to transport trains, and it was the major mode of transportation for the United States. It's been used since the early 1800s. Same problem, kind of. So steel railroad track, wooden sleepers, or the beams that hold the railroad track. So you have the load from the locomotive, moments about the sleepers. And the thing that we're going to be looking at today specifically, look right here. So the sleepers are 1.79 feet apart. That's important to mention. So for this project, we are going to find the largest load, the value P, that the locomotive can place onto the beam, in this case, from our class, since we are doing beams in chapter 5 and 6 and 4, that can be applied at a point between the two wooden beams. So our model here, to add a little bit of interest to the problem that we're analyzing, the force P is offset to the left on the beam. They are both pinned points, so it is statically determinate. And we have our giving and knowns, so maximum normal stress that the beam can take is 65 ksi. Our larging shearing stress is 39 ksi. And we are given the distances between A, B, and C, as well as the section modulus and the depth pulled from, I believe, Appendix E of our textbook for the beam used as railroad tracks, as well as the web thickness, also from the appendix. So here are the hand-done calculations that were used to solve this problem. And at first, we have our free body diagram similar to the one previous. And first we summed the moment about C and A to get our reaction forces at both A and C, our pin points. And then we found the shear forces at A and C in relation to P with our variable, and also at B. And then we found the moments at B, and then all of that information was plugged into our max normal stress and our max shearing stress equations, and our knowns were then plugged in at that point, and we found two values for P, one being 5,242 kips, and the other being 11,010 kips. So for the question that we were asking on the next slide. So with our results, given those two values, we will pick the lower of the two values because that will result in a failure of the railroad track. So we are limited by our normal stress, not our shear stress, at 5,242 kips. And you can see with our shear and moment diagrams where how those are visually laid out between the two sleepers. So looking back at the given data that we received from the or the knowns from the problem that we're looking at between the two sleepers, all of our normal stresses, the distances between A and B and C, section modulus, web thickness, depth, things that we use to find the force P that could be put at B. But what we are really going to use now to find the beam deflection between A and C at point B is the moment of inertia. And for the railroad track that we are using, the beam in this case is given as 0.0052 feet to the fourth. And our Young's modulus, also given for this equation, is 210 GPa. So the handwritten work that was required to find the beam deflection is as follows. We just have a beam deflection formula for the case that it is. So we have beam deflection, or maximum beam deflection, equals PB multiplied by 3L squared, which is the total distance between A and C, minus 4B squared. So B is the distance from B to C, the longer portion of the beam itself, and L is the total distance. And then on the denominator, we have 48 multiplied by Young's modulus, and then by the moment of inertia. So putting those, the values that we found in the last project, plus the known values into the equation. So looking here, our shear stress peak is 11,010.72 kips. And our distance from B to C is 1.253 feet. And our distance, the total distance, is given on the assumptions page as 1.79 feet. Sorry. So going back to our work, we have our P value multiplied by the distance between B and C, and then in parentheses, 3 times L, 1.783, 1.79 squared, minus 4 times the, again, distance from B to C squared. And then on the denominator, we have 48 multiplied by, and for our purposes, we transitioned and changed GPa to pascals, the base unit. So it's 210 multiplied by 10 to the 9th, multiplied by our moment of inertia, 0.0052. And our total beam deflection at point B comes out to be 8.57 times 10 to the negative 7th feet.